Hello everyone, welcome back. If you remember, in the last class we were discussing about the use of hydrometer for evaluating the particle size distribution of fine grained soils, and in this direction we also talked about the sedimentation analysis and the use of Stokes law to find the relationship between the effective height He and the diameter of the particular particle. And then we started talking about hydrometer. We saw the hydrometer and then we tried to understand the different parts of the hydrometer, how the readings look like, and then how the specific gravity of the solution or the material in question can be calculated using the reading of the hydrometer. So, now let us start talking about the steps that are involved in using the hydrometer for particle size distribution analysis. So, the first step is that we will take 50 gram of oven dried sample of soil which are passing 75 micron. So, we are trying to analyze those finer particles or soil that passes 75 micron, particle distribution of which we cannot analyze using a conventional sieve analysis. Okay. And then we take this 50 gram of oven dried sample and we will mix it with 100 ml of dispersing agent. So, usually if 40 gram per liter of concentration of sodium hexametaphosphate solution is used as the dispersing agent, and the use of this dispersing agent is to prevent flocculation of the soil particles. If you remember, we talked that the soil particles of very smaller size, they have surface charge and also they have the tendency to agglomerate. So, this sodium hexametaphosphate solution, it will help in keeping this particle separated from each other. So, that is the use of this dispersing agent. Okay. So, we will mix it with 100 ml of dispersing agent and we will stir the mixture using a mechanical mixer. So, we will stir it for a few minutes, ensuring that the sodium hexametaphosphate solution has properly deflocculated the fine grained soils. Then this sample is then transferred to a measuring jar. So, I have the measuring jar as an example with me. So, this is a typical measuring jar. So, this mixture which I have just prepared, I will put it in the measuring jar, and then this entire measuring jar I will fill with distilled water such that the total volume is 1000 ml. Alright. So, this is what I will do. So, the sample is transferred to the measuring jar and distilled water is added to make 1000 ml of the suspension. So, the total volume will be 1000 ml. Then we will shake the jar upside down to make the suspension homogeneous, because you see we have filled the soil with the dispersing agent in this particular jar, and then we added distilled water from the top. So, it may happen the soil particles are still settled at the bottom or are randomly moving in the jar, but it is not homogeneous in nature. So, once we have filled it with 1000 ml, we have a cap here, a rubber cap, we can close it and we will just shake it in this way upside down, so that the entire soil particles which we will have occupies equal volume at different levels. When I say equal volume at different levels, which means after doing this step, the suspension will look something like this. So, soil particles of different sizes will be distributed homogeneously in that particular jar, and this is at t equal to 0. We have not yet started the experiment. Okay. So, at t equal to 0, since it is in homogeneous condition, so if you take any particular area, okay, or two different areas, let us say two different areas you take. So, here the weight of the solid per unit volume of the suspension, and here the weight of solid per unit volume of the suspension will be equal to each other, okay, which also means that these two layers will have same value of density or same value of specific gravity, is not it. So, that means that at t equal to 0, the specific gravity is equal at all different locations in the measuring jar. Since we are talking about per unit volume of the suspension, so at t equal to 0, if I am interested to know the weight of the soil per unit volume, I already know this because I know what is the weight of total soil I have used to prepare the suspension, and I know the total volume of the cylinder is 1000 ml. At each layer the ratio will be same. So, it can be directly calculated as weight of the total soil taken divided by 1000 ml. Okay. So, this is again one of the important points to make, because this step we will use in the calculation of percent finer when we are going for the calculation. This I will discuss in the next slide. Okay. Okay. So, before I proceed to the next slide, one more important point which I should mention here is, so you try to imagine this is at t equal to 0. What will happen after some time? Let us say t equal to t, what will happen? So, at t equal to t, you can now understand, because we have discussed about the sedimentation analysis and Stokes law, that these larger particles will move faster than the smaller particles. So, at t equal to t, you will have smaller particles here and larger particles will be moving down. So, which means that the suspension will no longer be homogeneous. In other words, I can say that after some time, the lower part of the jar will have higher density in comparison to the upper part, which means there will be a non-uniform distribution of specific gravity of the solution at different times, and on the upper layer the specific gravity or the density will be less in comparison to what we will see in the lower part. All right. So, then what we will do, once we have shaken the jar, we have made the suspension homogeneous in nature. You just try to imagine that if you have the suspension here, then what I will do, I will very slowly insert this hydrometer inside the suspension and I will leave it. So, it will stay stable at the particular position depending on the type of suspension, and then I will record the reading. So, I have the hydrometer here, okay, and it is giving me the value of specific gravity at this particular point at the middle, and accordingly, if this is the top surface of the solution, so I will note the reading here. This reading which I am seeing here, this represents the specific gravity. I am getting the value of R, which I can use to calculate the specific gravity, as I know that this is equal to 1 plus, as I discussed in the previous slide, 1 plus R by 1000. All right. So, this I know, but I do not know this particular height. The reading which I am taking, this is not the height reading, this is the reading to get this specific gravity. This is how the hydrometer was calibrated, but I do not know what is the effective height at this particular position. So, what manufacturers do, they usually calibrate the hydrometer using a distilled water to find the relationship between reading R and the depth HE, because you see, depending on the specific gravity of different location in the suspension, this hydrometer at different time will occupy different positions. All right. At different positions, it is going to give different values of R, and different values of R will have different values of effective height. So, they already do this background work while calibrating the hydrometer, and they will give us a relationship between the value of R and the corresponding HE. So, for any value of R, I will know that what is the value of HE. All right. So, HE also we can get if we know the value of R. Again, this is something which you have to remember. Okay. Just for your information, though we are not discussing in detail about the calibration process, but during the calibration they do a derivation in which we will see, or you can see, that the value of effective height is basically a function of the length of a hydrometer bulb, which is this one. Okay. The height of the submerged neck. So, if in the experiment, if this is the solution and this is the position of the hydrometer, then this is the length of the neck. Okay. This is the length of the neck submerged inside the water, and the volume of the hydrometer bulb. So, in this they assume that the volume of the hydrometer is only equal to the volume of the hydrometer bulb, and they do not consider the small volume of the stem of the hydrometer. Anyways, we are not going to discuss in detail about the calibration process. Then the hydrometer reading, and therefore the value of HE keeps on changing with time. I hope you understand why, because as I mentioned, in the suspension larger particles will settle. So, if let us say t equal to 0, this is the position of the hydrometer. Okay. Let us say t equal to 0, this is the position of the hydrometer, and this is the reading which you get. All right. So, this is where the hydrometer is taking the reading. So, as time progresses, larger particles start settling down. Okay. The top of this particular jar will have lower density in comparison to the bottom part. Therefore, and you see the weight of the bulb is fixed, the weight of the hydrometer is fixed. So, the buoyant force will keep on reducing with time. The buoyant force will keep on reducing with time. Once the buoyant force reduce, the hydrometer will start moving down. Because of the weight, the hydrometer will start going down. Alright. So, therefore, now you can understand that at different times we will have different values of He which will keep changing depending on the density, how the density is changing. So, what we do in this process, we take the hydrometer reading at different times. The typical time are 30 second. After 30 second we will take the reading, after 1 minute, 2 minute, 4 minutes. After 4 minutes what we will do, we will take out the, because our next reading is going to be after 1 hour, which is a considerable period of time. So, we very slowly take out the hydrometer from the suspension, and this hydrometer we dip basically in another jar having only distilled water, so that we can have the cleaning of the hydrometer. And then just 20 seconds before our next time, that is 1 hour, we will remove it from the distilled water jar and put it in the suspension which we are trying to analyze. Okay. So, this we will do keep doing, that is keeping it in the distilled water, again keep it in the suspension, and at different times, like after 1 hour we will take the reading, again remove it, keep it in the distilled water, then just 20 seconds before 2 hours we will put it inside the jar, again take the reading, take it out, put it in the distilled water, again just 20 seconds before 4 hours we will put it, and so on. Okay. So, we will do it, and then we will keep recording the reading. So, which means that with time I will have different readings of the hydrometer, which means different specific gravity values, and corresponding to different readings I will also have the different values of He. Alright. Now, an important step is to make correction to the hydrometer reading. So, at different times, though I have got the reading, let us say that the reading is R. So, this R I have to correct. And why are these corrections required? The first correction is due to the meniscus, second is due to the temperature, and third is due to the dispersion. So, why is a meniscus correction required? Because when you dip the hydrometer in the suspension, the reading which you take, because of the surface tension, the suspension will move upwards. Alright. So, when you see it with the eye, and the suspension is opaque in nature. So, you take only the top surface, this is the reading you are taking, but the actual reading should be this particular reading. Alright. So, which means, and you see the reading of the hydrometer increases as you move from top to bottom. Okay. So, when you are taking the reading, it is actually taking a lower reading, but ideally you should have taken a higher reading. Okay. Which means that this correction should be positive in nature. And how do you find out that how much correction is required? It is very simple. You just take the jar, you take a distilled water which is not opaque, you can see everything, you dip the hydrometer in it. Here also you will get the because of the surface tension you will get the change in meniscus, but here you will be able to see it very clearly because it is a clear solution. So, you just note down the difference, and the same difference you use it as a correction in the reading for the suspension. Okay. So, this is first correction. The second correction is the temperature correction. We all know that with increase in temperature, the density of any suspension will usually reduce. So, if the density decreases, try to understand it in this way, if the density decreases, the buoyant force will decrease, so the hydrometer will move down. When the hydrometer move down, okay, before I proceed further, just like to mention that the hydrometer is usually the standard temperature is 27 degrees Celsius. So, let us say that at 27 degrees Celsius this was the reading I am supposed to have, but since the temperature has increased, the hydrometer has moved down, I am recording actually this reading. Okay. But I should have recorded this, which means from 2 I should have gone to 4. So, therefore, again if the temperature is higher than 27 degrees Celsius, then the correction factor will be additive in nature, I have to add it. Okay. Similarly, if the temperature is lower, my hydrometer will move upwards, then it should have been at 27 degrees Celsius. So, the correction factor will be negative. Okay. So, this temperature corrections which we have discussed, that this is usually provided by the manufacturer. So, we will have a correction chart for different temperatures. If it is above 27 degree, as I said, the correction factors will be additive in nature. If it is lower, then it will be subtractive in nature, and this is usually provided by the manufacturer. The next correction is basically the dispersive agent correction, because the suspension which we are looking at does not only have the soil particles which we are trying to analyze, it rather also has the dispersing agent present in it. So, we have to remove the effect of dispersing agent so that we get the correct reading. Now, the addition of dispersing agent, it will obviously increase the density of the suspension. So, you can understand that if the density of the suspension increases, the buoyant force will basically increase, the hydrometer will move up in comparison to what it should have been without the dispersing agent. Okay. So, here we get a higher reading, but the reading should have been smaller. So, the correction is negative in nature. Okay. So, to get this particular correction, again we can use the distilled water as the reference. So, what we can do, we can use a distilled water with 1000 ml, let us say, take the reading of the hydrometer here. Okay. Then what we can do, we can use because you see here what we have done in our suspension. If you remember in this particular slide, that here we had 100 ml of dispersing agent. Okay. So, the similar quantity by volume we can use here, and then the amount of distilled water will be reduced such that the total volume is again 1000 ml. So, this total volume we will keep constant and we will add equal amount of dispersing agent as we are using in the experiment, and then again we will do the hydrometer analysis and we will take the reading, and the difference in this reading will give me the correction factor to be applied. Okay. So, and finally, we will calculate the corrected reading of the hydrometer, which will be the reading R, and then with all the corrections, the meniscus correction, the temperature correction and the dispersing agent correction. Okay. So, I hope these steps are clear to you, and now we move forward to calculate, to see the calculation of percent passing or percent finer and how it is related to the hydrometer reading. So, let us first define percent finer. So, percent finer is weight of the soil particles smaller than size d divided by the total weight of the soil particles into 100. I hope you understand this, right, that this is what we discussed, that percent passing is the weight of soil particles smaller than size d. Even in the sieve analysis, the example which we took, that we are taking, let us say, 100 gram of soil, passing it through the sieve, and we are noting out how much soil is passing. So, this fraction we are trying to determine. So, weight of soil particles smaller than size d divided by total weight of soil particles into 100. Now, when we are doing the hydrometer analysis, what will be this formula in the terms of the different heights or effective height which we get from the reading of the hydrometer. So, I will try to explain it in this way. See, at t equal to 0, all the portions of the hydrometer, as we discussed, will have the same density because the distribution of the material is homogeneous. But let us say that we are looking at d. Now, again I would like to make a comment here that d is again related to He. So, if you know He, you also know d at any time t. Okay. So, let us say I am looking at a particle d. So, and I am trying to find out that what is the weight of soil particle smaller than size d. So, at what time will I get that? I will get it at a time when basically at a time t, when this particle of size d or these particles of size d have just crossed that particular level at which I am doing the measurement He, or I am noting down the hydrometer reading, and only the smaller particles are above it. only the smaller particles are above it. Okay. In the homogeneous condition, these particles were here, but after some time, because larger particle will settle down, these particles have come here. Okay. So, weight of the soil particles smaller than size d I will get at time t equal to t. So, weight of the solids at t equal to t, because you see if I am trying to find out percent finer, then let us say this is W1, W2, W3, W4. So, percent finer for size d using in this particular picture, it will be W2 plus W3 plus W4 divided by W1 plus W2 plus W3 plus W4, and this denominator, this was present at what time? At t equal to 0, you see, when everything was in this particular line. Alright. So, I hope I will just give you some time to see this picture again, and then this is what I have written here, and then I have tried to explain this with respect to different times. Alright. So, this is what I am trying to find. This I will get at time t equal to t, this I will get corresponding to the height he at t equal to t, and the denominator I will get corresponding to the height he at t equal to 0. Okay. So, I hope this is the most important part which you need to understand in order to be comfortable with the analysis we are doing using the hydrometer. Okay. So, I hope this is clear to you. Now, as I mentioned, he corresponds to a particular size d, which we have seen the relationship using the sedimentation equation. So, if you have the reading of the hydrometer, you have the value of he. If you have the value of he, you also have the value of d. So, these three are known just by knowing the value of RC. Alright. Okay. So, now usually this equation is represented as weight per unit volume of the suspension, because we do not know at this particular position what is the exact volume of the suspension. Okay. So, the same equation or the same weight of solids at t equal to t I can express in terms of weight of solids per unit volume at t equal to t, per unit volume of the suspension, and this is what I have written here. Okay. So, percent finer is equal to weight of the solids in the layer per unit volume of the layer divided by total weight of the soil, and you see this why I have written this, because this is at t equal to 0. And if you remember, we have discussed in previous slides that at t equal to 0, different locations will have the same density, which is actually equal to the weight of soil sample divided by the total volume of the suspension, which is 1000 ml, which we have taken. Alright. Now, our target, in order to calculate percent finer, this is already known to us. So, our target is to calculate this. So, now I will try to explain that how this calculation can be done, okay, how we can obtain the numerator. So, as I mentioned that the specific gravity using the hydrometer reading can be calculated as 1 plus r by 1000, let us say. Okay. So, specific gravity is what? An RC, because this is the corrected reading. Specific gravity of, and just I will draw it again to explain you that we are trying to see this case here. Okay. I am trying to see this case here, and I am trying to see the weight of solids per unit volume of the layer in this particular case, the numerator, okay, t equal to t. So, specific gravity is basically equal to gamma of this particular layer divided by the unit weight of water, the basic definition. So, gamma of layer can be written as weight of the layer divided by the volume of the particular layer divided by gamma w. Okay. So, this I can write as 1 by gamma w. Okay. So, weight of layer is basically equal to weight of the solid present in the layer plus weight of the water present in the layer divided by the volume of the layer. This weight is equal to the summation of this weight 1 by gamma w. So, this I can write as separating weight of water by volume of layer plus weight of solid by volume of layer. Weight of water I can write as gamma of water into volume of water divided by volume of layer plus weight of solid divided by volume of layer. Okay. Volume of water I can write as volume of the layer minus volume of the solids, is not it. So, this is what I am writing 1 by gamma W. So, this is gamma W into volume of layer minus volume of solid divided by volume of layer, weight of solid by volume of layer. I am just simplifying this expression now, separating it. This is gamma W into volume of layer divided by volume of layer minus gamma W into volume of solid by volume of layer plus volume of solid divided by volume of layer. Okay. So, if we take gamma W as 1, then I get, I am just putting gamma W as 1. So, I get this as 1 minus volume of solid divided by volume of layer plus weight of solid divided by volume of layer. Now, volume of solid, if I know the specific gravity of the soil, so volume of the solid I can write as weight of solid divided by the specific gravity of solid. Now, here I should know the specific gravity of solid also. Okay. So, 1 minus this is weight of solid divided by the specific gravity of solid into volume of layer plus weight of solid divided by volume of layer. Okay. So, if I simplify this, I can write this as 1 plus weight of solid by volume of layer multiplied by 1 minus 1 by GS, alright. So, if you come here, then this is 1 plus RC by 100,000 sorry is equal to 1 plus WS by VL, which is nothing but 1000, is not it? Oh sorry, not 1000, this is VL only, VL, I am sorry, VL into G1 minus 1 by GS, is not it? I hope this is straightforward. From here, if I want to find weight of solid by volume of layer, I will get it as RC by 1000 into G of solid divided by G of solid minus 1. Alright. So, this is the final expression which we get here. I know the specific gravity of the soil for which I am doing this particular test. I know the value of RC, and therefore, I know I can calculate the value of WS by VL at different times t, okay, different time t, because RC will change with t, alright. So, at different time t, since I have the value of RC, I can calculate WS by VL, and therefore, at different time t, I can calculate percent finer that particular size DI, okay. I can calculate the percent finer corresponding to that particular size DI. So, as I said that numerator is related to the reading of the hydrometer, and this is what we have derived. So, if I put this expression here, I get percent finer as G by G minus 1 into RC, which depends on time, divided by the weight of soil into 100, very simple. So, in the actual experiment, what kind of table will I have? For example, I can have time. At different time, I will have the actual reading or the value of R of the hydrometer. Then I will have the corrected reading RC here, applying all the corrections of the 3 parameters we discussed. Since we have RC, we also have the effective height based on the hydrometer calibration. Once I have the HE value, I also have the value of D, because I know the this is based on the Stokes law. G of the soil I have to find out from laboratory test. I know the weight of soil which I have used, and I can calculate the percent finer. So, at different time, different RC, different HE, different D, GS will remain same, then WS will remains same, and correspondingly percent finer I can calculate. Okay. So, I hope that this is clear, that how we use the hydrometer analysis to calculate the percent finer corresponding to different sizes, and then we plot it in the combined curve. So, this blue part of the curve which you are seeing is from the sieve size analysis, this red part on the top is from the hydrometer analysis, and then we will shift this curve here by applying a correction to this reading, because this is a continuous process, is not it. For example, if 75 micron passing is x percent, so this percentage I will multiply with x percent to get these particular values, alright. So, I will just shift the curve corresponding to the total material passing 75 micron, and I will get the sieve size distribution, total sieve size distribution curve, which is this one. Okay. Alright. So, I hope that this is clear to you. Now, few concluding points about the particle size distribution concepts which we have discussed. That gradation curve, as I mentioned, gives an indication about the classification of soil. We will see about that, about the classification process. It tells us about the distribution of different sizes for adequacy of any layer, because for any given layer there can be requirement of some particle size distribution. So, I have to ensure that the soil or the material which I am using, does it have that required criteria, alright. So, it has a critical role on the mechanical behavior of the soil, because let us say if you have a soil mass where you have only single sized particles, that particular type of layer or that particular type of soil will have very high permeability, but very low stability. Okay. On the other hand, if the voids between larger particles are filled by smaller particles, which means you have a soil where you have different sizes of aggregate particles, that type of soil mass will have low permeability, but if it will have higher stability. So, the mechanical behavior is also directly related to the particle size distribution of the soil particles. It gives an indication about the ability or possibility of the moisture retention and absorption, depending on the amount of, let us say, finer particles we will have, amount of, let us say, a clay particle which will have in the soil mass. So, that will tell me how this material will behave when moisture changes or moisture comes in contact with that particular soil mass. Okay. Shape also influences the shear strength and permeability, which I just discussed, that if you have better interlocking, which means you have particles of different sizes, but the permeability will be less. So, shear strength and permeability can be opposite to each other. Well, there are typical shapes which are defined by looking at the sieve size distribution curve. So, these are usually categorized in 3 classes. We have well graded soil. So, this is a well graded soil. You see, you have particles of different sizes in this particular soil mass, all for different sizes of particles are present. Okay. Then you have gap graded samples. So, this is a gap graded where you have some materials finer particles, you have coarser particles, but these particles are missing, which means this size is same material passing, this size same material passing, this size same material passing, this size same material passing. So, this particular size range is missing in this particular type of particle size distribution. And then we have poorly graded or uniformly graded, which you see here. Here you have only particles of limited size. For example, you do not have these sizes here, you do not have these sizes here, you have only particle of this size. So, these are mostly single sized particle, and that is why this will have high permeability, but less stability, and it is not very desirable from the point of view of appropriate strength in the structure. Now, this uniformity, I mean the distribution of the particle, they can also be quantified. Now, this is what we are discussing visually. You see the shape looks like this, the shape looks like that, but this shape can also be quantified using different parameters. For example, commonly 2 different parameters are being used, that is uniformity coefficient Cu and coefficient of curvature Cc. So, this is the definition or formula for Cu and Cc. So, Cu is d60 by d10. Now, what is d60? D60 is the size corresponding to which 60% of the material is passing. Let us see this curve. So, I will just draw a straight line here. So, in the well graded structure this is 60, and in the poorly graded structure this is D60. Okay. So, this is D60 in these two curves, and similarly D10 is the size D corresponding to which 10% of the material is passing. So, if you come here and just draw a line, so this is D10 for the well graded structure, and this is D10 for the poorly graded structure. I will just use a different color to set the difference. Alright. Now, just by looking at the curve, what you can say? Let us say I want to do some analysis for CU and try to tell something about or quantify something about the curve. So, you see in case of well graded structure the value of CU will be higher, because D60 and D10 will be separated from each other by some amount, alright. But in case of poorly graded structure they will be very close to each other, which means the ratio of D60 by D10 will be less, alright. So, this is again one indication. So, based on this already we have some specifications existing that tells us about the particle size distribution or quantify the particle size distribution of the curve. Similarly, we have Cc, another parameter which is defined as D30 square divided by D10 into D60. Okay. For example, if it is a well graded structure, then as I said the value of Cu will be higher. If it is a gravel, it is greater than 4, for sand greater than 6. If it is a uniformly graded or poorly graded, it is usually less, because you do not have many particle sizes in that particular curve. Similarly, the value of Cc ranges from 1 to 3 for well graded structure, and it is usually less than 1 for poorly graded structures. This is all about the particle size distribution, and we will stop here today, and in the next class we will take upon a new topic, that is consistency of soil, and we will discuss about it. Thank you.